Hello, my name is Steve Cho from IDAS Lab at Seoul National University. During our last session, we talked about the introduction to AI agents. We framed agentic AI as the next frontier in artificial intelligence, evolving from perception and generative AI to become an autonomous problem solver. Defining an AI agent as a software system that uses AI to pursue goals and complete tasks on behalf of users. Today we will go over the fundamental components of multi-agent system, define the types of problems they solve, and explore various collaboration strategies and communication structures that agents use to work together. We will start off with the background for large language models and multi-agent systems, then move on to the key components of the multi-agent systems for problem definitions. Then we will talk about collaboration types and strategies and communication structures. We will conclude with the key takeaways from growing concerns in multi-agent system. First, for a brief introduction to large language models. So with the recent rapid advancements in large language models, they are demonstrating superhuman performance on a variety of tasks. For example, prominent models like OpenAI GPT, Meta's Llama, or even Google's Gemini series, these are trained on a massive text corpora with parameters in the billions or even trillions. So this approach has enabled them to achieve excellent performance in many areas, including creative writing, reasoning, and decision making. But however, it's been pointed out that LLMs are not unconditionally superior. They have inherent limitations. So the key examples include the hallucination and their autoregressive nature and issues related to scaling laws. So the autoregressive nature refers to the LLM's fast thinking, its intuitive pattern-based characteristics. So this means it often falls short in the slow thinking tasks that require such as analytical reasoning, planning, or revision, or error corrections. And scaling laws mean that as you increase the model size, the performance improvement you get for the required resources diminishes. So in other words, it becomes resource inefficient. So to address these large language models, such limitations, we have begun using larger language models as agents equipped with external tools and a planning agenda. So by using these large language model based agents, we can break down such complex tasks and solve them more in terms of systematic way. This approach aims for collective intelligence objective, which aligns with research in the multi-agent systems and collaborative AI. So the concept of the multi-agent system is actually inspired by how humans use those teamworks or dividing a single task into specialized areas to be handled collectively. If we look at the example of a multi-agent system, suppose a user asks, why is the cryptocurrency more sustainable than the fiat currency? The example of this multi-agent system shown here is designed to answer this by using two collaboration channels. So before we go on, the term collaboration channel, it will be used frequently in this presentation. You can think of this term as of a single channel as a space where the multiple agents interact to each other. For example, the first collaboration channel here is a space where a support agent and an opposed agent interact and debate the user's question. Here, the opposing agent's role is to continuously challenge the supporting agent's claims unless they are backed by solid information or evidence. In the second collaboration channel, the opposed agent takes the user's question and breaks it down into several different perspectives. So for example, here there are inquiry on the environmental impact or inquiry on stability and so on. So it then tasks various research agents with investigating each specific perspective and providing answers. So the opposed agent then synthesizes the information and evidence gathered from these diverse viewpoints to form its own comprehensive opinion. So this is an example of how agents in two collaboration channels can debate and discuss to generate a final response for the users. So we've reviewed the existing LLMs and an example of a multi-agent system with the cryptocurrency, much more sustainable than the fiat currency. Now, I'll focus on the following key areas here. First, I'll provide a brief background on the multi-agent systems. Then, I'll introduce the various collaboration types, strategies, and communication structures that have been presented in the multi-agent research. Finally, we'll conclude with or by discussing the existing challenges in multi-agent systems and what kind of research directions are being pursued to solve them. So let's start with the background of the multi-agent system. So multi-agent system can be broken down into four key components here. So the first is agent, which has been introduced with a rather grand definition as LLM-based agent. It's the core actors with roles, capabilities, behaviors, and knowledge models. And the second is environment. So this refers to the context in which the agents interact. To simply put, you can think of it as a specific task for which you are using the multi-agent system. So the environment can be divided by domain, and within the specific domain, it can be further divided by the task. So the proper definition would be the external world where agents are situated in and can sense and act upon. And the third is interaction. So interaction refers to the manner in which the agents interact, which I'll explain later. And the proper definition is the communications between agents happen with the standard agent communication languages. And organization, lastly, is a similar to interaction, but to be more precise, if interaction is about how agents communicate, the organization is about the broader perspective of how agents are arranged within the collaboration channel. And the proper definition is where the agents either have a hierarchical control or organize based on the emergent behaviors. And now, let's define what constitutes an agent within the multi-agent system. So to construct an LLM-based agent, the model to be used as an agent must be defined, and this model, which we'll call M, consists of an architecture, memory, and adapters. So the architecture is basically the foundational model of the agent, and the agent's specific memory typically refers to things like system prompts that can guide the LLM and store the context. So for example, there are system prompt in the GPT or the memory modules that are specifically for the agents. And lastly, the adapter refers to the mechanisms that allow the agent to utilize external knowledge or tools to aid its judgment. The objective, we'll call small o, is used to guide the agent's overall actions. So whether it's a task or any subtask divided from the task, you can think of the objective as the agent's reason for being within the multi-agent system. The term environment is used a bit differently here than the previously mentioned environment in the overall components of the multi-agent system. So here it refers to the information or some conditions given to an agent to carry out its assigned objective. So for example, some research calls it as a context window, likely because the information provided and the task to be performed are all supplied within the LLM's context window. And finally, we have the input and output. So these are just a systematic data set that goes into the model to output the desired result for some task. So overall, you can see that an LLM-based agent is defined as a foundational model and an objective to perform a task and a context window as an environment and its inputs and outputs. Now, to expand this to the definition of a multi-agent system, so there are several components here which can be combined into the equation, where A is a LLM-based agents, where N is a number of agents, and OCollab is a collective set of goals that may be partitioned into unique objectives. And a shared environment from which agents receive contextual data is defined as E, and C is a set of collaboration channels that facilitate interactions among the agents and their inputs and outputs. So to simply put, a multi-agent system is a method of taking an input and producing an output using previously defined agents. So to define it more clearly, it's a defined number of agents operate within their designated or assigned collaboration channels. According to their respective objectives, they receive input tailored to those objectives, interact with other agents within the channel, and produce outputs that match their objectives. So these outputs are then aggregated to derive a single final result. So looking more closely, the output of a single collaboration channel can be defined as such, where CJ is a single collaboration channel. So within that collaboration channel, if we call each agent AI, where the input and the context provided to that agent, and the resulting output, YJ, from the agent performing its assigned objective, and it can be visualized in such equation. As such, to summarize the final output, YCollab, the values of YJ from each collaboration channel are integrated using the defined interaction methods within the multi-agent system. So this ultimately becomes the YCollab. So to explain again using the example diagram that I provided previously, so in the multi-agent system, there are two collaboration channels, as I mentioned. Taking the first channel as an example, the user's question enters the first collaboration channel, then the support agent has the objective of sharing its opinion with the opposed agent. Then the opposed agent has two objectives. First, to listen to the support agent's opinion and decide whether to oppose it, and second, to interact with other research agents to gather information from the various perspectives and consolidate an opinion. So this illustrates the formal definition: a defined number of agents in their assigned channels act on their objectives with the relevant inputs, interact with others, and produce outputs that are then combined to generate a final result. So now we're going to talk about the collaboration types. So these collaboration types are techniques that define how agents will interact at the communication level. So they can be broadly divided into three different categories, which first is cooperation, and then competition, and co-opetition. So typically the cooperation are used for the academic writing support system, and the competition, it's often used in the court simulation, and co-opetition, it's mainly used in the policy making systems. So if we first look at the cooperation, it is a method where a single large objective is broken down into several sub-objectives, and each agent is assigned a suitable sub-objective. So agents align their individual objectives with shared collective goal working together to achieve a mutually beneficial outcome. So you can think of it as a way for several subset objectives to collaborate to achieve one main objective. So each agent has a necessary expertise to carry out its sub-objective. However, on a larger scope, it's not always individual agents that carry out these sub-objectives. Sometimes an entire collaboration channel is assigned to a single sub-objective. So a couple of drawbacks uh, or considerations need to take in for using cooperation is that there are frequent communication and there are some multiple collaboration channels between agents, but it can lead to a increased computational cost and complexity. And it's pretty much dependent on the reliability and performance of individual agents, as the failure of one agent or more agents can negatively impact the entire system. And those negative impact, as such example, would be infinite conversation loop or amplified hallucination. So, for example, a paper called Agent Verse divides the goal of build into sub-objectives like expert recruitment, decision making, action execution, and evaluation. It then assigns one collaboration channel per sub-objective. Within each collaboration channel, there are several agents collaborate to carry out their respective sub-objectives. So in the expert recruitment, there's a system or the collaboration channel that assesses each agent and assigns a expertise to that agent. And these group of agents uh, performs a debate, the multi-turn debate, and process the collaborated decision making. And each agent then is assigned with the actions or the set of actions that was decided from the decision making. And given that, agents build new state and you evaluate basically if the final completion of the work is similar to the new state that they built. So to summarize, the cooperation involves dividing a complex task into a procedural steps to enable the collaboration among agents. So many studies besides agent first have shown that this collaborative technique can significantly boost the performance on tasks, but there are some few points to be careful about. So first, depending on the number of sub-objectives, the cooperation method itself can be resource inefficient and may not perform well. Therefore, the optimal number of objectives must be considered. Second, when the objectives are divided, they are generally processed sequentially. So, as I mentioned, if a subobjective is not properly executed in the middle of the process, it can lead to a significant drop in the overall task performance. Next is a competition. So in competition, rather than having sub-goals, a single objective is divided into multiple perspectives, and each agent is assigned one of these perspectives as its objective. So for example, while the sub-objectives in cooperation feel like a team effort to sequentially reach a final goal, the objective in a competition feels more like agents competing against each other to achieve their own objective. So agents prioritize their individual goals, which may clash with or oppose the objectives of others, introducing an element of rivalry. And it basically encourages agents to develop the advanced reasoning and more creative problem solving. However, the competitive collaboration channels can be overtaken by a single agent counterparts with the strong prompts, and it might have a never-ending argument if all the agents have their own strong opinions. So, for example, there's a paper called LLM Arena. So it looks very complex at first, but it's also simple here. It's a study designed to verify the performance of the competition technique in the 7 different competitive game environments. So if you look at the tic-tac-toe game in the upper left here, the agents in that game environment compete to be the first to place three of their masks on the board. So basically, the conclusion is that the competition technique shows good performance in the reasoning and also in the risk assessments. So, in this way, other studies related to debates or difficult question and answering tasks also state that the competition technique helps agents in a multi-agent system with reasoning and creative problem solving. However, it has been also found that, as I mentioned, the one agent can become dominant depending on the model's performance or such as system prompting techniques, which increases the probability of a incorrect reasoning. And furthermore, if the agents are evenly matched, there's a never-ending argument which can occur where the competition goes on indefinitely. So as a result, research is emerging on when to stop the competition and how agents should compromise or negotiate. So finally, co-opetition is a technique that appropriately uses both cooperation and competition to improve the task performance. So it's a method where all agents cooperate to achieve a single objective, but within the system, they compete with each other to contribute the best possible result to the shared objective. So there's also a competition method inspired by the mixture of expert MOE framework. So the MOE structure is an basically ensemble method that combines multiple models. So mixture of experts consists of several sub-models called experts, and each trained to specialize in a specific task. And there's a gating, or originally called routing structure, acts like a manager. So considering the input data and forwarding it to the most optimal expert. So in this way, the expert selection process uses a competition structure, and the selected expert agents then cooperate to perform the task. So moving on to collaboration strategy, which deals with how to design the interactions between agents. The first strategy I will introduce is a rule-based protocol, which focuses on agents to interact only through the defined rules. So predefined rules are often adopted in agent systems with a sequential communication structures, and it ensures that agents coordinate their actions according to the system-wide constraints on the acceptable inputs. So rule-based protocols basically mimics the human collaborative dynamics where, for example, a peer review inspired collaboration mechanism, it uses a predefined rules to allow agents to critique, revise, and refine each other's outputs. And rule-based strategies ensure straightforward implementation and facilitate debugging, as system behavior can be easily traced back to a specific rules. And also, it's particularly efficient for tasks with well-defined procedures and limited variability, such as consensus seeking and navigation. So there are some moments where you can use it where to prevent situations like the never-ending argument mentioned in the competition section, where you can limit the number of rounds in a debate. If the specified number of rounds is exceeded, the debate stops and a majority vote is taken. So rule-based protocols can be defined at various levels of agent system, and if defined well, they can yield good results in both performance and efficiency. So another one is a role-based protocol. So the role-based protocol is a technique that enhances task performance by assigning a specific roles to each agent. Taking a paper called MetaGPT as an example, MetaGPT adopted a role-based protocol to implement a standard operating procedure called SOP for software code generation in multi-agent system. So first it divides the main objective into sub-objectives, and sets up the domain expert agents for each subobjective. Each domain expert agent performs its task according to its subobjective, and at the end, the project is inspected to check for acceptance. So coming back, as you can see from the example, this role-based protocol is frequently used in tasks where the roles to be assigned are very clear. That's why it's also a widely used technique in the medical domain. So a key advantage of the role-based protocol is reusability, where a domain expert agent developed for one task can simply be brought over and used in another task if well trained. Finally, to discuss the communication structure, you can think of the communication structure as what determines whether a certain agent in the system is given more authority or decision-making power, or whether all agents have equal authority in performing the task. So usually in a centralized structure, so-called the subordinate agents perform tasks related to the objective, and a central agent with decision-making power consolidates the information from each subordinate agent to determine the output for the given input. So for example, in a debate environment, there's a judge agent that listens to the all opinions of each agent and decides which agent's opinion is more suitable and reasonable for the given topic. Similar to that, there's a doctor synthesizing a treatment methods or diagnostic conclusions from a real multidisciplinary team meeting to make the final judgment also falls under the centralized structure. So a decentralized structure, unlike a centralized one, is a structure where you can set up a desired agents and collaboration channels in real time. Since the collaboration channels interact with each other in a structure without the central agent, it has a key advantage where in a centralized structure, if the central agents, if they fail, the task cannot proceed properly. But in contrast, in a decentralized structure, if one of the designated agents or collaboration channels fail, the task can still continue, but it has a disadvantage of potentially being resource inefficient due to calling agents in a real time, and the number of communications can be somewhat inefficiently large because there's no central agent to control it. Finally, I would like to conclude by talking about the problems and considerations that are being raised across the board in the multi-agent systems. First and foremost, a problem that is commonly raised in any multi-agent research is the issue of efficiency. Personally, I don't think there are many research topics where the trade-off between performance and efficiency is as intuitive and clear as in multi-agent systems. The structure usually involves dividing a single task into multiple objectives and then uh, using an optimal collaboration method to produce a result. So here, there are many points to consider for efficiency. So what size model to adopt for the LLM-based agents, how many collaboration channels to use for the divided objectives, how many agents to use within a single channel, what collaboration technique to use in each channel, and so on and so forth. In fact, the concepts of the techniques used in the multi-agent systems are very easy to understand, but how to utilize them within the system seems to be a topic that requires a lot of thought and experimentation. So in conclusion, the performance efficiency trade-off in a multi-agent system is really clear, and an optimal system setting that can be balanced is necessary. So with that final remark, I will conclude my seminar, and thank you for listening.